It is 6 p.m., but participants are yet to join. So we'll wait for a couple of more minutes before we start. Good evening. This is the final week for the live sessions of the course uh, AE03 Computational Science and Engineering. This course is taught by Professor Ashok Dey from the Department of Aerospace Engineering at the Indian Institute of Technology, Kanpur. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. So in this session, we'll be looking exclusively at PDEs. We also had at least one session before where we looked at the theoretical aspects of and analyzed the techniques for solving PDEs, which was mostly by separation of variables. We looked at a few cases where it could not be applied directly, and how to say transform under certain cases a problem into one where separation of variables was applicable. We also looked at the Laplace equation and at Neumann and Dirichlet boundary conditions. We also examined the situations under which Neumann uh, problem may have a solution and conditions under which it may not. So just as a prelude to this session, we'll first solve a heat equation question. So the details of this have already been discussed in the lectures by Professor Day. We'll directly get to solving it. So here we are asked that the standard heat equation on a rod of length 10 units, and initially the rod has a temperature distribution which is given as a function of the distance. Now the boundary conditions at either end are supplied to us. So at say the left end it's 80 units and at the right it's 20 units. And while we are to find a transient solution to this situation, but also to plot the trend of the solution, that is our temperature distribution and its evolution with time for say a few time steps, just to gauge an idea of how the temperature really evolves across the rod. So let's get started. So the heat equation is already given to us. So it's del U del T equals alpha square del T U del x2. The 1D heat equation in its say simplest form. And the boundary conditions given to us are U at 0 comma T. That is at say the left hand is 80 and U at 10 comma T. The right hand is fixed at 20 for all T greater than 0. And the initial conditions supplied to us, the initial distribution of temperature at time t equals 0 is the function, sorry about that, is the function 10x, where 0 less than equal to x is than equal to 10. So typically the heat equation is also solved by separation of variables type of formulation. Let's apply it and see what happens. So let us just say that the variable u, which is a function of both location and time, can be separated into a function exclusively of location and a function exclusively of time. So your usual separation of variables. And if we apply the initial conditions to it, so say here 0 comma t is 80, this would imply that x at 0 and t at n time t is 80, which would imply that at any time t, the function is equal to 80 by x at 0. Now in simpler situations where say this RHS is simply equal to 0, now this can be very simply resolved just by say assuming that x at 0 is 0, and then we have no trouble because then t, the function capital T, which is only depending on time, can be anything. But here this is not the case, and here this comes out to be a constant because the numerator is a constant. The function at x at small x equal to 0 will be a constant. So this will be a constant. And this is a problem because we just see that in our transient solution, the time-dependent function capital T is turning out to be a constant, which may be true in a trivial case, but this cannot be a general solution. So we run into a problem. Again, the way to solve it is to say perturb the solution or to introduce an additional term just to accommodate these non-homogeneous boundary conditions. So we simply introduce one more term. So x and t remain as such, and we introduce another term, phi. Let's see how the problem transforms with this introduction. So now this is a function of only x, mind you. So now del u del t is only del capital U del t because phi is a function of x only, whereas del t u del x2, that is now we are evaluating the LHS and RHS of the standard heat equation, is equal to del 2 capital U del x2 plus phi double prime of x. So far so good. If we compare it to the standard form of the heat equation given here, del Hs del capital U del T equals alpha square del 2 capital U del x2 plus phi double prime of x. Now compare this with del U del T equals alpha square del 2U del x2. There is only one term on the RHS. There is no other function of x or t, and this may pose a problem. So to maintain consistency, we may assume that the second derivative of phi is 0, and basically we are constructing our function basing in this assumption, and we'll construct it in a fashion so that it accommodates the boundary and initial conditions. What this will imply is that the first derivative of phi was some constant, say d1, and the function phi itself is a linear function, so some d1x plus d2. Let us say match this or contest this with the initial conditions given to us and see if it can accommodate all of them. So the first initial condition, sorry, the boundary condition, u at 0 comma t is 80, which implies that u at 0 comma t plus phi at 0 is 80. Now we are already familiar with solving, say, equations of the standard form. The heat equation where this right side is homogeneous, that is, say, something equivalent to your 0 comma t is 0. So we already know how to solve this. Can we adapt our formulation to such a step? Yes, we can. So say if we assume, and this is just for the sake of convenience because then we can reduce it to a problem whose solution we already know. So if we assume that u at 0 comma t is 0, this will imply that phi at 0 is 80, and we already know what phi is like, so phi of x is some d1x plus d2. So phi at 0 equals 80 implies d2 is 80. Similarly, let's check for the other boundary condition. U at 10 comma t is 20. So u at 10 comma t is 20, which implies that capital U at 10 comma t plus phi at 10 is equal to 20. And again, just to reduce it to a problem we already know how to solve, if for the sake of convenience we assume that u at 10 comma t is 0, then phi at 10 must be 20 as per our formulation. And if phi at phi of x is d1x plus 80, this implies that, sorry, and if phi at 10 is 20, this will imply that d1 times 10 plus 80 is 20, or 10 d1, or we can write directly d1 is minus 6. Therefore, we have our function phi of x minus 6x plus 80. We also have an initial condition given to us, which is u at x comma 0 is 10x, which gives us the initial distribution of temperature at the start of observation t equals 0. So u at x comma 0 is equal to 10x. And as per our formulation, capital U x comma 0 plus phi x is 10x, which implies that u at x comma 0 phi x is minus 6x plus 80 is 10x, which would in turn imply that 16x minus 80. Or suddenly we have the initial condition in terms of, or we may even write it as initial condition for u at x equal to 0, which is 16x minus 80. And what this does is, now we have a few familiar conditions staring at us. We have the heat equation, 1D heat equation that we are trying to solve, and we have the left hand held at 0, the right hand side held at 0, as well as the initial distribution of temperature as a function of x itself. So this is a problem we are already familiar with. Now we can say reframe the given question in terms of u only. So the problem for you would be del u del t is equal to alpha square del to u del x2, given the boundary conditions. You had 0 comma t is 0, you had 10 comma t is 0 for all t greater than 0, and u at x comma 0 is equal to 16x minus 80. This is a problem we are already familiar with, so let's just solve it very quickly. So again, applying separation of variables. And it better work this time because we did this exercise to reduce the original problem to a separation of variables step formulation. So let now u of x comma t equal sum capital X, which is only a function of x, times sum capital T, which is a function of t only. And del u del t in this case will turn out to be xt prime, del to u del x2 would turn out to be x double prime. And if you put this back into the original equation, del u del t equals alpha square del to u del x2 implies xt prime equals alpha square x double prime t, which implies that x double prime by x equals t prime by alpha square t equal to minus lambda. The negative sign is chosen by convention, and lambda is the separation constant. Using the boundary conditions, u at 0 comma t is 0 would imply that x at 0 times t at t is 0, and since t at all times cannot be 0, as this will only lead to a trivial solution, x at 0 must be 0. Similarly, for the other boundary, u at 10 comma t is 0, which will imply that x at 10 times t at all t is 0. And since this cannot be equal to trivially 0, so x at 10 must also be 0. X double prime by x equals minus lambda, which implies that x double prime plus lambda x, sorry, they are looking the same. Lambda x is equal to 0 with x at 0 equal to 0 and x at 10 equal to 0. So we are already familiar with stum Liouville problems of this kind, which we encountered in a previous live session. So I'll write the answer directly. Of course, we know how to do it. We apply the three cases where lambda is uh, either positive, negative, or 0, and see what that gives us. For this case, the eigenvalues are lambda n is equal to n square pi square by 10 square, or n square pi square by 100, and the eigenfunctions are xn equals sine n pi x by L. Here L is already given, so it will be sine n pi x by 10. Similarly, let us solve for t now. So t prime by alpha square t. Sorry about that. T prime by alpha square t is equal to minus lambda, which implies that t prime plus lambda alpha square t is 0. The value of lambda is already known to us. So t prime plus n square pi square by 100 alpha square t is equal to 0. And well, this is a pretty straightforward ODE to solve. P turns out to be e power minus n square pi square by 100 alpha square t. And so it's independent, so just write n. Thus, the function un, which is actually equal to xntn, turns out to be e power minus n square pi square by 100 alpha square t. I just wrote the t term before, does not matter, times sine n pi by 10x. This is just say one of the solution, but the general solution for you is the sum of all such a un. So starting from n equals 1 to infinity, some coefficient cn times un, so e power minus n square pi square by 100 alpha square t sine n pi by 10 x. Again, from the initial conditions, we may evaluate the value of cn u at x comma 0 is 16x minus 80, which is equal to some n equals 1 to infinity cn times e power 0 is simply 1 sine n pi by 10 x. But this is simply the Fourier sine series expansion of this 16x minus 80. I also write it. And the formula for the coefficient in this case is already available with us. So we know that Cn will then turn out to be 2 by L, which is 2 by 10 in this case, 0 to L, so 0 to 10, fx sine n pi by Lx, so n pi by 10x dx. And now let us integrate this and hope to not make any mistakes, where we do have ample space. So 1 by 5, just I'll just break it, so 0 to 10, 16x times sine n pi by 10x dx minus 80 times integral 0 to 10 sine n pi by 10x dx. The first one will involve integration by parts. So if we take x equals u, so integration by parts, and here I'm taking u equals x and v equals sine n pi by 10x. You can try doing it the reverse way, see if it is any easier. So this will turn out to be u into integral v dx, which will be minus cos n pi by 10x by n pi by 10. Uh, why am I writing this? And this will be evaluated between 0 and 10 and minus integral of differential of u, which is only 1, into integral of vds, which then turns out to be cos n pi by 10x by n pi by 10 whole dx. And for this one, it's rather simple, minus 80 times minus 1 cos n pi by 10x by n pi by 10 evaluated between 0 and 10. The first term turns out to be 10 minus cos n pi is, yeah, the other term will turn into a sine by n pi by 10 squared from 0 and 10. And this last term will be cos n pi minus 1. 80 times cos n pi minus 1 by n pi by 10. We will have 1600. Cos n pi also is minus 1 power n. So you can integrate the minus 1 over there. So this can be 1600 minus 1 power n plus 1 minus 1 power n from cos n pi. And this additional negative here. So minus 1 power n plus 1 by n pi. This term sin n pi is 0, sin 0 is 0. So the second term will go to 0. And the third term will be 800. Cos n pi again is minus 1 power n. So minus 1 power n minus 1 by n pi. 1600 by 5 is 320 times minus 1 power n plus 1 by n pi plus 800 by 5 is 160 minus 1 power n minus 1 by n pi. And if we add these two, one is minus 1 power n, one is minus or 1. So if I put it as minus 320 minus 1 power n plus 160 minus 1 power n minus 160 by n pi. This will turn out to be minus 160 power times minus 1 power n minus 160 by n pi, or simply 160 times minus 1 power n plus 1 minus 1 by n pi. Okay, this is just the coefficient Cn. Our solution is u of xt is the sum n equals 1 to infinity Cn, so 160 by n pi minus 1 power n plus 1 minus 1 times e power minus n square pi square by 100 n square pi square by 100 alpha square t times sin n pi by 10x. Sin n pi by 10. This is the solution to the question. Again, we can do one more simplification based on what exponent n we are dealing with, because we have a minus 1 power n plus 1 minus 1. So whenever n is odd, minus 1 power n plus 1 will be even. So n plus 1 will be even. So this will be 1 minus 1 will be equal to 0 when n is even. And n plus 1 will be odd. Minus 1 power odd will be minus 1. This is equal minus 2. So we can only choose this for even n, because in other case it will be 0 anyway. And if I multiply by minus 2, this will make it minus 320 by n pi e power minus n square pi square by 100 alpha square t times sine n pi by 10x. So this is the final solution we're looking for. We saw how the question was not really one where we could apply the separation of variables directly, but just by making or constructing a suitable function for you and say adding that additional function phi of x, we are able to reduce it to a form which we're already familiar with, and we could apply the separation of variables technique. Now, to finish it, let us try and get an idea of what the temperature profiles would be like. So, if I just sketch, say, okay, that's not a straight line. Let this represent u at xt, and this represent uh, x. And here, let us have x equals 0 and at some distance. Let this be x equals 10 units. Similarly, on the y-axis, so we had 20 and 80. Let this be u equals 20, and initially it was 10x. So maybe 100 as well. Now, at the very beginning, at t equal to 0, the solution given to us or the initial condition given to us is that uh, u at x comma 0 is 10x. So at t equal to 0, the distribution should be, or temperature distribution should be linear. And this will simply be a straight line joining the origin to this point. Okay, not the most accurate. Still not accurate. Final try and then I'll let it be. Let it be. So this is at, maybe I can color code it. So at t equal to 0, this is what the characteristics would be like. And we know that after an infinitely long time, that is when the system has reached steady state, it will simply be, say, have a linear distribution of temperature from one end to the other. So the left hand is always held at 80 degrees, the right is held at 20. So eventually, if I use, say, purple or red, eventually it will be something like the left hand will be at 80, right hand will be at 20. So the red one can be for a sufficiently long time, so maybe t tending to infinity. And in between, we'll find the temperature profiles to resemble something like this. So at a very small time after t equal to 0, the temperature profile will not differ much. Then again, the left hand side will be held at 80, the right hand side will be held at 20. So these must be satisfied. So one probable way it can look like is, so this is some T1, and as we move ahead in time, we'll approach the steady state characteristics. This can be some T2. What more colors do we have? This can be T3, where T1 is less than T2 is less than T3. So eventually, this is T tending to infinity. This is T equal to 0. This is T1, T2, and T3. So this rough sketch gives you an approximate idea of how the temperature profiles will evolve with time. Initially, it will be linear from the left hand to the right, based on the type of function given to us. Here in this case, it was a linear function. Eventually, the steady state distribution will again be linear from the left hand side to the right hand side. And in between, the temperature will evolve in the fashion shown. Now let us proceed to the numerical aspects of it. So just for the sake of completion, I mentioned what elliptic PDEs are. Of course, we're already familiar with them. So in this case, the Poisson equation, that is nabla square u of xy is equal to del 2u del x to xy plus del 2u del y to xy, which is equal to some function f of x and y with some given initial conditions and boundary. If f and g are both continuous, then there is a unique solution to this equation. And to implement this numerically, we discretize the solution domain available to us. In this step, The first thing to do would be to choose integers in NM to define the step sizes along the x and the y axes. They may also chosen to be the same, but for the general case, let us assume that these step sizes are different, and we'll simply say as a form a grid in our solution domain and solve for these mesh points rather than solving for the continuum. So all these lines at xi and yi are called the grid lines, and their intersections are the mesh points. And for each mesh point, we can use the Taylor series in variable x and xi to generate the centered difference formula. In one of the previous sessions, we looked at the forward difference, the backward difference, and the center difference, and we also examined what advantages and drawbacks each of them might have. The center difference formulation is available to us. Again, for the y-axis, we can do the same thing utilizing the Taylor series and again generate the center difference formula, which is given to us in 12.3. This will help us express the Poisson equation in the difference form with some error, which is of order h square, and the boundary conditions can also be expressed similarly, such as u at x naught yj can be equal to some given function g of x naught yj. Similarly for the other ends at y naught, ym, and at xm. And utilizing the method of finite differences, this can be expressed as shown here. So 2 times h by k square plus 1 wij minus wi plus 1j plus wi minus 1j. We see that different mesh points are utilized in this equation. Minus h square by k wij plus 1 plus wij minus 1 equals minus h square, some function of xi and yj. Now, this typical equation will involve approximations to the function u of xy at these mesh points that we saw. So, xi minus 1 yj, xi yj, xi plus 1 yj, xi yj minus 1, and xi yj plus 1. And we can visualize it here. So, to obtain the information for this point in the center shown in blue, we'll utilize information from these other points which surround it. 1, 2, 3, and 4. And in essence, this will produce an n minus 1 m minus 1 cross n minus 1 m minus 1 linear system with the unknowns being the approximations w to our function u of xy at the interior mesh points. And the linear system involving these unknowns is expressed from metric calculations more efficiently following a different labeling procedure, which is just illustrated here for your purpose. It is optional to stick to it or not. What this will accomplish is simply label the mesh points from left to right and top to bottom as shown here. You can reverse it, that is, you may start at some bottom extreme, label this as P1, P2, and go on. As long as it is consistent, the outcome will be the same. Now, we are asked to perform a simple discretization exercise and find the steady state distribution in a thin square metal plate with dimensions zero point 0.5 by zero point 0.5 and also equal step sizes. So we are dividing each dimension into 4 parts. Any two adjacent boundaries are held at 0 degrees Celsius, and the heat on the boundaries increases linearly from 0 degrees Celsius at one corner to 100 degrees Celsius, where the sides are meeting. So let us try to reproduce a grid similar to the one shown here and see how things are. Let this be x and this be y. We have to divide it into 4 subdomains. Again, it says that two adjacent boundaries are held at zero. So just for the sake of convenience, let us assume that it's the one along the axis. Again, this will be zero point 0.5, and this dimension here is zero point 0.5 as well. And in the other two boundaries, it increases linearly from 0 degree at one end to 100 degree at the other. If you formulate that, it will turn out to be, let us just confirm. So at x equal to 0, the temperature is 0, and at x equals zero point 0.5 along this line, the temperature is 100. Same for this other edge here. So this formulation works. And let us just label the interior points. So P1, P2, and so on. So now we have the solution domain visualized. In this case, the boundary conditions will be u at 0, sorry, x or 0 comma y is 0, u at x comma 0 is 0, u at zero point 0.5 comma y is 200y, and u at x comma zero point 0.5 is 200. Now, in the difference equation form, it will put it in equation 12.4. Okay, it is too cumbersome to write. But if you put it in the equation 12.4, what we'll end up with is 4wij minus wi plus 1 comma j minus wi minus 1 comma j minus wi comma j minus 1 minus wi comma j plus 1 is equal to 0. That is, the information of the ith and jth node is expressed in terms of the neighboring nodes. So say for P5, I have the information in terms of P2, P4, P6, and P8. And this is valid for I equals 1, 2, 3, and j equals 1, 2, and 3. And if we try to say express it for each of these nodes that we have listed here, it will look something like this. So for P1, it will look like 4w1 minus w2 minus w4 is equal to w03 plus w14 for node P2. 4w2 minus w3 minus w1 minus w5 is equal to w24. So we have two indices on the RHS here. They refer to the x and y positions in the grid. We have only one index on the left hand side because say w1 refers to the approximation at p1, w22 at p2, and so on. This is based on the relabeling scheme that we saw here. Similarly, p3 can be rewritten as 4w3 minus w2 minus w6 into w43 plus w34 we are doing this exercise extensively just to see how the solution will be framed. We'll just frame the matrix and leave it at that because now we are already familiar with methods to solve such linear systems. So it is worthwhile to write out all of the points. For P4, it will be 4W4 minus W5 minus W1 minus W7 W0, comma 2. For P5, 4W5 minus W6 minus W4 minus W2 minus W8 is equal to 0. For P6, this will turn out to be 4W6 minus W5 minus W3 minus W9 equals W4, comma 2. For P7, 4W7 minus W8 minus W4 W0, comma 1 plus W1, comma 0. Similarly for P8, and finally for P9. The right hand side, of course, incorporate the boundary conditions and agree with them. And the linear system that will eventually end up having to solve will look something like this. So based on the coefficients we have obtained here, four minus one, zero minus one, zero 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 zero. Okay, I should have some more space. Four minus one, zero minus one, zero 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 minus one, four minus one, zero. 0 minus 1, 4, 0, 0. It is a sparse matrix, the terms being either minus 1, 4, if not 0, minus 1, 0, 0, 0, 4 minus 1, 0 minus 1. Did I miss something? Minus 1, 0, 0. Okay. 4 minus 1, 0 minus 1, 0, 0. 0 minus 1, 0 minus 1, 4 minus 1, 0 minus 1, 0, 0, 0. Minus 1, 0, minus 1, 4, 0, 0, minus 1, 0, 0, 0, minus 1, 0, 0, 4 minus 1, 0, 4 zeros, minus 1, 0, minus 1, 4, minus 1, and finally, this is the coefficient matrix. The variable vector will have all the w's. So w1, 2, 3, 4, 5, 6, 7, 8, and 9. And then the RHS. But where do the RHS come from? They come from the boundary conditions. The boundary conditions will imply that W1, 0 is W2, 0, W3 comma 0, 0 comma 1, 0 comma 2, 0 comma 3 is 0. So these are the W's at this X and Y edges. For instance, this is W1 comma 0, W2 comma 0 and 3 comma 0, which are all equal to 0. This is W1 comma 0. Oh, sorry, this is W1 comma 0, 2 comma 0 and 3 comma 0. These ones are W0 comma 1, 0 comma 2 and 0 comma 3. Since they lie on the X and Y axis, which we have in this case chosen to be 0, they will all be 0. Similarly, based on the other boundary condition for the sides, W1 comma 4 equals W4 comma 1 is 25, W2 comma 4 will equal W4 comma 2, which will equal 50, and W3 comma 4, W4 comma 3 shall equal 75. So we see that the nodes are the temperature distribution is symmetric at the nodes. So we incorporate this into our solution matrix. Again, this is an exercise best done with a computer, so we'll just leave it by forming the matrix and see how our discretization step can lead to the solution. One, two, three, four, five, six, seven, eight, nine. And upon solving this linear system, we'll end up with the solution at all of the nodes. To implement this in a code, I'll also supply the pseudocode for a Poisson equation which uses a finite difference method. This is a really involved code. Again, I borrowed it from reputable sources and I hope it works. I have checked it, it worked for me, but there was some time when I used it. So just implement it and let me know in case you run into any errors. So the objective for such a code would be to approximate the solution to the standard Poisson equation for a given domain, say x lying between A and B. I just write it. So del 2u del x2 plus del 2u del y2 equals some function of x and y, where the domain is defined as a less than equal to x less than equal to b and c less than equal to y less than equal to d. The boundary conditions are prescribed in this form. U at xy is some function of xy if x equals to a or x equals to b and y is lying within the domain, and u at xy is equal to g of xy if y is equal to c or y equals d, that is at the boundaries of this rectangular domain, and x lies within the domain. First, the inputs. These would be the domain bound endpoints. So A, B, C, and D. Also, we would like to know how many parts we want to divide the domain into. So how many divisions for the x-axis, how many divisions for the y-axis. So M and and this code is designed so that there are at least three subdivisions. The maximum tolerance denoted by the variable tol, after which is the acceptable accuracy of solution, and the maximum number of iterations they're willing to perform. And the output which you would expect from such a code. is the approximations or are the approximations wij to the exact solution uxi yj for sorry I equals 1 2 and n minus 1 and j equals 1 2 m minus 1 at I equals n and j equals m as well as for I equals 0 and j equals to 0 they are already prescribed in form of the boundary condition, or if this is not possible, if we are unable to reach the desired tolerance within the given number of iterations, then such a message, the message that the maximum number of iterations has been exceeded. And let us get to the code. So first we'll discretize our domain. So we'll set the step sizes. Along the x-axis, it will be b minus a by n. Along the y-axis, say it's denoted by k, d minus c by m. Now we'll construct the mesh points. So for I equals 1 to n, n minus 1, we set xi equals a plus ih. Similarly, on the y-axis, for j equals 1 to m minus 1, we set yj equals c plus j k. I'll just comment what this step is doing. And then a nested loop for j equals 1 to m minus 1, we set wij equal to 0. So we basically say assign an initial value so that it does not take a garbage value by default. We assign a default value to each of the mesh points. In the fifth step, we set lambda equals h square by k square. This lambda is a parameter we encountered in the difference formulation of this problem. We set mu equals twice 1 plus lambda. And we set the parameter L equals 1. Now, step 6. Well, this counter L is less than equal to the maximum number of iterations n, we do the subsequent steps, and those would be some, okay, 20 steps. But these are basically the Gauss-Seidel iterations. So Gauss-Seidel method is being implemented in the following steps. Step 7. You may also choose a different solution scheme, one that might be more suited to your, say, particular problem or particular case. But Gauss-Seidel is like a failsafe. We usually use it. We set Z equals minus x square f of x1 y m minus 1 plus g a y m minus 1 plus lambda g x1 comma d plus lambda w1 m minus 2 plus w2 m minus 1. This entire quantity by mu. We find the norm of this with respect to w1 m minus 1, then set w1 m minus 1 equal to z. All of these steps are the general algorithm, constitute the general algorithm for the Gauss-Seidel iterations. They have no supplementary meaning apart from that. I equals to 3 n minus 2 can be set z equals minus square of xi ym minus 1 plus lambda g xi comma d plus wi minus 1 m minus 1 plus wi plus 1 m minus 1 plus lambda wi m minus 2 by the quantity mu. We have a conditional check if the absolute value of wi m minus 1 minus z is greater than the norm that we previously calculated, then set norm equal to this. So wi m minus 1 minus z. Then iteratively set wi m minus 1 equal to z. Now within the loop, so maybe I'll write it here. We set z equals again minus x square f x m minus 1 y m minus 1 plus g times b y m minus 1 plus lambda g x n minus 1 comma d plus w n minus 2 n minus 1 plus lambda w n minus 1 m minus 2 by the quantity mu. Again, check if the norm is less than this or not. Then set norm equal to this. Then again, update the value of uh, wn minus 1, mn minus 1. We'll do this a couple more times. Again, these are just the steps for a standard Gauss-Seidel iteration. If you have a pre-written function of the Gauss-Seidel, you can simply call it and use it. Till 2, we do the steps 11 to 13. Step 11 involves setting z equals minus h square f of x1 comma yj plus g of a comma yj plus lambda w1 comma j plus 1 plus lambda w1 comma j minus 1 plus w2 comma j by mu. Again checking for the norm. So if w1 comma j minus z greater than norm, then set the norm equal to w1 comma j minus z and update the value of wi comma j. This is repeated a few more times. Now let's say no nested loop for I within j. Square root of xi comma yj plus wi minus 1 comma j plus lambda wi comma j plus 1 plus wi plus 1 comma j plus lambda wi comma j minus 1 by mu. Check for the norm. Update the value of wij. Z equals minus x square f of x1 y1 plus g of a y1 plus lambda g x1 comma c plus lambda w1 comma 2 plus w2 comma 1 by mu. If w1 comma 1 minus z is greater than the norm, then again set norm equal to w1 comma 1 minus z and update w1 comma 1. Sorry, I might have made a mistake here. Yeah, well, 20 steps, so you're bound to make some mistakes, I guess. Let's rewrite it. So, f of n minus 1 comma yj, g of b yj plus wn minus 2 comma j plus lambda wn minus 1 comma j plus 1 plus lambda wn minus 1 j minus 1 by mu. We check for the norm. When z is greater than the norm, and set norm equal to this quantity wn minus 1 comma j minus z and update the value of wn minus 1 comma j. Now we come out of this loop. Set z equals minus h square f of x1 comma y1 plus g a comma y1 plus lambda g x1 comma c plus lambda w1 comma 2 plus w2 comma 1 by mu, and if nano w1 comma 1 minus z is greater than the null, we update the null. 1 comma 1 minus z also updates the value of w1 comma 1 equals to 3 till n minus 2. Something similar. Z equals minus h square f of xi comma y1 plus lambda g xi comma c plus wy minus 1 comma 1 plus lambda wi comma 2 wi plus 1 comma 1 by mu if wi comma 1 minus z is greater than the norm, then set the norm equal to it, update the value wi comma 1. Set z equals minus h square f of x n minus 1 comma y plus g of b comma y plus lambda gx n minus 1 comma c plus w n minus 2 comma 1 plus lambda w n minus 1 comma 2 by mu if w n minus 1 comma 1 minus z is greater than the null, set the norm equal to it and update its value. Okay, we're out of space, maybe I'll just continue somewhere else. Now, if this norm is less than equal to our desired tolerance, then do steps 18 and 19. So for step 18, for I equals 1 to n minus 1, then for j equals 1 to m minus 1, we output xi, yj, and wij. Step 19 is simply to stop. That is, the procedure was successful. An option for a page here. Oh yes. Okay. If not, we go to step 20. Where we set L equals L plus 1 and go to the next iteration. And finally, if the solution could not be achieved in the maximum number of iterations, we'll output the message. The maximum number of iterations were exceeded. Stop. That was quite intense. Let us quickly move to parabolic PDEs. Again, we already looked at the heat equation or the diffusion equation and looked at what common forms the boundary condition and the initial conditions can take. Now they may be discretized, or the domain of the parabolic PD may be discretized using a forward difference algorithm, such as one shown here, where each Wij will approximate the temperature or the quantity U at x of xi and tj, and it can further be simplified. Once we have the solutions at each of the edges, so in terms of the function, so W00, W10, and W10, so these are coming from the initial conditions. We can generate the next T row, that is, we have this row at T equal to 0. We generate the next row at T equals T plus some time step, which was K. In X, say we have the time step of H. We just saw how these S and K are calculated based on the choice of number of divisions we want to make along those dimensions. And since it's a forward differentiation scheme, it is explicit in nature. We already discussed how the forward difference schemes are explicit. That is, the unknown quantity is expressed in terms of all known quantities and can be calculated by algebraic operations. The backward difference schemes were implicit in nature. That is, the equation defining the known quantity had the known quantity itself on both sides. Under certain cases, it might be possible to simplify it into an algebraic equation and obtain the solution via an explicit fashion. But in other cases, it might not be possible. Thus, generally, from an implicit formulation, we cannot obtain the solution of the variable directly. However, in this case, it is explicit, and thus the solution can be incorporated into an m-1 cross m-1 matrix, which will be tridiagonal. And once we incorporate the initial condition W0, the approximate solution can be obtained as Wj is equal to this matrix times Wj minus 1. So once we have the information of one step, we can generate the information for the next step. Wj will be obtained from Wj minus 1 by simple matrix multiplication, and this is referred to as the forward difference method. And graphically, if it is to be shown, then the information and this blue cross can be obtained by a formulation which utilizes the information at the previous time step Tj for from these three neighboring nodes. This method is conditionally stable. We already examined how the forward differentiation scheme might not always be stable, and the method will converge to a solution with the rate of convergence of the order of k plus h square, provided the quantity alpha square k by h square is less than or equal to half. Alpha was defined here. Alpha, okay, it is defined somewhere. I cannot find it. Oh, alpha square is from original heat equation. So the method is conditionally stable. It will be stable only if the product of alpha square k by h square is less than or equal to half. And of course, the required continuity conditions on the solution are met. If not, the solution will not converge and the method will be unstable. However, because of their implicit nature, the backward differences scheme are unconditionally stable, as we already saw. And to obtain this method or to derive it, we consider an implicit difference method that results from using the backward difference coefficients. And the backward difference method results in a formulation of this kind: Wij minus Wij minus 1 by k minus alpha square Wi plus 1j minus 2wij plus wi minus 1 comma j by h square equals 0. Now this backward difference method involves the mesh points x, these ones. So when we want to calculate information for the blue cross here, we want we will use information from these neighboring mesh points. And one thing you can directly observe is that here we are moving up in time. So say this was t equal to 0, this was some t1, t2, t3. And what we are doing is we have solution at each time step we are solving for the mesh points along x. Utilizing this, we are solving for the mesh points at the next time step. Utilizing that information, we solve for the next time step and so on. So when we are solving for the tj plus 1th time step, we are utilizing the information that's already available to us from the jth time step. And based on its location, xi plus 1, we'll use the information from, so for xi comma t j plus 1, we need u x I minus 1 comma tj, which is this one right here, u xi comma tj, which is the one directly at its bottom, and u xi plus 1 comma tj, which is this one, all at the previous time step, and one directly below it and the other two on either side. But they are already known to us, and so we can find an explicit formulation. In this case, however, we proceed in a similar fashion. So we first solve for t equals to 0. We find the information at each of these nodes along the entire x. Then we move up to say t equals the next time step t1, then t2 and so on. But when we are solving for the jth time step, we need information. So for u at xi comma tj, we need this one is known, which is u of xi comma tj minus 1. But the other ones are not known. That is u xi minus 1 comma tj and u xi plus 1 comma tj. Say I'm solving for this second node available to me. Maybe I can have some information from the boundary condition for this first one. But what about this neighbor? The right hand neighbor information is simply not available to me. And thus, this method cannot give us explicit solutions just by some algebraic manipulation. They have to be solved iteratively. Again, in a similar fashion, by defining the quantity lambda, the backward difference method will reduce to an equation like this, and it will have the given matrix representation in 1213. That is AWJ is equal to WJ minus 1. The matrix A is positive definite and strictly diagonally dominant, as well as being tridiagonal. So it can be solved by known conventional computation methods. And I'll quickly share a pseudocode for solving the heat equation using the backward difference method. This is not as long as the previous one. So we already discussed the standard formulation of the heat equation. I'm not going into that. Let us start with the inputs. This will be a 1D code. So we have only one endpoint, L, the maximum time T, the constant alpha, and the integers m greater than equal to 3 and n greater than equal to 1. And what these m and n are? So, so this is not a 1D code, it's a 2D code. Approximation wij2. You, no, it is a 1D code, sorry, because it has only one endpoint for each I equals 1 to m minus 1 and j equals to 1 to n. Why m minus 1? Because at the end m we'll already know the uh, state of the variable from the boundary condition. Similarly, at I equal to 0, it will be known to us. At j equals to 0, which is actually the time index, we'll know from the initial condition. So those are not needed. Now, in the first step, we set h equals L by m. This is the step size along the length of the given part or length of the domain, one dimensional domain. K equals T by m and lambda equals alpha square K by h square. In the second step, for I equals 1 to 2 to m minus 1, we set wi equals f of ih. Step 3. So starting here, we'll solve the tridiagonal matrix. So steps 3 to 11, solve a tridiagonal linear system. This is one of the algorithms to solve it. There might be others which you might find more suitable given the type of problem you're dealing with. So you are free to choose your own. So set L1 equals 1 plus 2 lambda, E1 equals minus lambda by L1. Then for I equals 2, 3 to m minus 2, we set L equals 1 plus 2 lambda plus lambda times u I minus 1 and ui equals minus lambda by li. In the fifth step, we set L m minus 1 is equal to 1 plus 2 lambda plus lambda u times m minus 2. Step 6, for j equals 1 to n, we do the steps 7 to 11. Step 7 is to set t equals jk. That is the current time step, and we set z1 equals w1 by l1. Step 8, for I equals 2, 3 to m minus 1, we set zi is equal to wi plus lambda z minus I by Li. Step 9, we set Wm minus 1 is equal to z m minus 1. Step 10, for I equals m minus 2, m minus 3 till 1, we set Wi is equal to zi minus ui times wi plus 1. And step 11, we output the time step t, also commented, so t is equal to tj. For I equals 1, 2, 2, m minus 1, we set x is equal to ih and also output corresponding temperature. Wi is actually wij. So this method will sequentially output the time step and the temperature at the various nodes. Then we move to the next time step. Again, spit out the temperatures at the various sequentially spit out the temperature at the various nodes and so on. And it is done in 11 steps. So the 12th step is to simply stop. Again, steps 3 to 11 are just an iterative way of solving the tridiagonal linear system by some standard algorithms such as TDMA or tridiagonal matrix algorithm. But you are free to choose any other method you might find more suitable to your problem. However, this might not be the most, say, efficient or the smartest way to do it. And there are methods which are shown to be more useful in certain cases. One of those is the Crank-Nicolson method. And here what we do is the forward difference formulation is averaged at the jth time step. And this will have the local truncation error of the order h square. The backward difference method is also averaged at the j plus 1th time step. It also has a local truncation error of the order of h square. And based on certain assumptions, we obtain the averaged difference method utilizing both the forward difference and the backward difference, which has local truncation error of the order k square plus h square. Why this is more preferable to say the error obtained in the simple backward difference scheme is something that is a known result, is a proven result, but beyond the scope of this present course. But for now, we'll just assume this as available knowledge that the truncation error of this order, k square plus h square, is more preferable. And that is why we applied these modifications to the forward and backward differencing schemes. We average them. And of course, the usual differentiability conditions have to be satisfied. And this modified method or average method is known as the Crank-Nicolson scheme. And in matrix form, it is represented as matrix A times Wj plus 1 is equal to matrix B times Wj, where the quantity lambda is defined as alpha square k by h square. Wj denotes has the elements W1j, 2j, Wm minus 1j at the tth time step, and the matrices A and B are defined here. And here is a visualization of the Crank-Nicolson method. So to find the information about the state of the system at this blue cross, we utilize information from these neighbors, both at the concurrent time step and from the time step before. The final section we look at are the hyperbolic PDEs, and perhaps the most straightforward or commonly encountered application of them has to do with the wave equation. And wave equation is generally defined in this fashion. So del T u del T2 as a function of x and t minus alpha square del 2u del x2, which are functions of x and t equal to 0. X lies between 0 and L, and t is equal to greater than 0, subject to the boundary conditions u at 0 comma t is equal to u at L comma t equal to 0. So both the boundary ends are actually nodes where the displacement is 0, and the initial condition u at x comma 0 is equal to fx, and also the initial position u at x comma 0 and the initial velocities. So del u del t at x comma 0 is equal to gx for all x lying between 0 and L. Alpha, of course, is a constant dependent on the physical conditions of the problem. Again, to discretize the domain of a hyperbolic PD, we again start by selecting a suitable integer and to divide our x-axis into the grid points. The step size h is then defined as equal to L by m. We also select a time step size k greater than 0, and the mesh points are then defined as xi is equal to ih and tj is equal to jk. Now at any interior mesh point which is away from the edges, the wave equation will take on the form del tu del t2 at xi tj minus alpha square del tu del x2 xi tj is equal to 0. And here if we apply the centered difference scheme up to the second partial derivatives, we come up with these formulations. Substituting these into the standard form of the wave equation at an interior node gives us this with an error term which is this 1 by 12 k square del 4u del t4 and so on. And if this error term is neglected, we end up with the familiar form of the wave equation wij plus 1 minus 2 wij plus wij minus 1 by k square minus alpha square wi plus 1j minus 2 wij plus wi minus 1j by h square is equal to 0. Again, we define the quantity lambda as alpha k by h, and then can rewrite the difference equation in this form. And the most advanced time step approximation to obtain wij plus 1 equals to 1 minus lambda square wij plus lambda square wi plus 1j plus wi minus 1j minus wi j minus 1. So again, utilizing information from the neighboring mesh points to find information at our point of interest. We incorporate the boundary conditions into this formulation as well as the initial conditions and rewrite it in matrix form. This will take the form given in 1222. So at j plus 1th time step for each of the nodes w1, w2, w3 and wm minus 1, we can obtain the information in terms of the two preceding time steps. So some matrix multiplied by the information at the jth time step, so w1j, w2j, wm minus 1j, and also information from the j minus 1s time step. So to calculate the information at one time step, we need information of the two prior time steps. And this is also written here. So the j plus 1th time step requires values from jth and j minus 1th time steps. And this produces a minor starting problem because values for j equal to 0 can be obtained directly, but values for j equal to 1 must be obtained from the initial velocity conditions. And there are many ways to do this. One approach is to replace del u del t by a forward difference approximation. and then solve it utilizing the initial bound conditions given, the initial velocity conditions given to us, and neglect the truncation error to obtain Wi comma 1 is equal to Wi comma 0 plus some kg times xi, where g is the function describing the initial condition. However, the truncation error, which is ignored in this case, has the order k, whereas the truncation error in our original formulation 1219 has the order k square. It has come as a subscript. I think this should be k square. And this is also visualized here. So to find or determine the information for the node represented by the blue cross, we need information of three neighboring nodes from the previous time step and at least one neighboring node from the time step one step prior. And to overcome this problem, we can also have an alternate approach where we expand u at xi comma t1. Rather than in a forward difference fashion, we use a second Maclaurin polynomial in T, and based on certain assumptions, this will produce an approximation with the error of order k cube. That is an order smaller than even our original formulation. This will be for the first time step wi1 is equal to wi0 plus kg times xi plus alpha square k square by 2 f double prime at xi. Again, if f is 4 continuous, but the second derivative of f is not readily available, we can use the difference equation to express it, and it can be simplified further without the need to explicitly calculate the second derivative. And then this equation 12.25 can be readily used to find the information at the first time step, which we had difficulty in obtaining. And once the information at the 0th time step and the first time step are available, we can definitely find information for all subsequent time steps. That is how we saw. We'll close by writing a pseudocode for this wave equation utilizing the finite difference formulation. Again, this is also relatively short and not as long as the one for the heat equation. Sorry, for the Poisson equation. So I'll just state the problem in standard form. So to approximate the solution, the wave equation del to u del t2 comma t minus alpha square del to u del x to x comma t is equal to 0 on the domain 0 as well. Sorry, on the domain 0 less than x less than L for the time 0 small less than t less than some maximum time t, subject to the boundary condition u at 0 comma t is equal to 0, u at L comma t is equal to 0. That is the displacement at the two nodes is always 0 at all times. And the initial condition u at x comma 0 is some function of x, the displacement condition and the velocity condition del u del t x comma 0 is again some function of x. And for such a code, the required inputs are the endpoint L, the maximum time the, the constant alpha, and the integers m greater than equal to 2 and n greater than equal to 2. The expected output would be the approximations wij to the displacements uxitj for each I equal to 0, 1 till m, and for the time steps equals 0, 1 till n. Now in the first step, we set the step sizes. So for the x dimension it is equal to L by m. For time it is equal to capital T by n. And we also define the quantity lambda, which is equal to k alpha by h. Now step 2, for j equals 1 to n, we set w0 comma j is 0 and w sorry, this should be w l comma j is 0. That is, we set the displacement at both the endpoints to be 0. Step 3, we set w at 0 comma 0, that is at the left node at t equal to 0 equals f comma 0, and w m comma 0 is equal to f at l. The fourth step, for I equals 1 to till m minus 1, we set w I comma 0 is equal to f at ih. That is, we set the initial conditions for all the other nodes. Based on our formulation, we define w I comma 1 is equal to 1 minus lambda square f at ih. So now we are trying to find the information for the first time step. We already have the information for the zeroth time step from the initial conditions, plus lambda square by 2 f of I plus 1 h plus f I minus 1 h plus kg ih. In step 5, once the information for this zeroth and first time steps are available, we start calculating information for the other nodes by the matrix multiplication. So for j equals 1 to till n minus 1, for each time step, for each uh, step size along the length of our domain, 1 to till m minus 1, we set w I comma j plus 1 equal to twice 1 minus lambda square wij plus lambda square wi plus 1 comma j plus wi minus 1 comma j minus wi comma j minus 1. So we find the value of the variable at our node of interest by utilizing information available to us from the neighboring nodes at the previous time steps. Step 6, for j equals 0, 1 till n, we set t equals jk, and then a nested loop for I equals 0, 1 till n. We again set x equals ih, and output for each position for each time what is the displacement. And this will complete the procedure. So the seventh step is to simply stop, and our procedure is complete. This was a pseudocode for solving the wave equation utilizing a finite difference formulation. The formulation is also expressed in the equation given to us, and it is my fervent hope that the pseudocodes will help you actually implement the theoretical discussions and the concepts discussed in the lectures into actual solvers, which may be used for practical problems. And that will bring us to the end of this session, as well as in general to the end of the live sessions for the course AE03 Computational Science and Engineering. This session is open for a couple of more minutes in case some participant joins in and has a question. Thank you for tuning in to the live sessions for the course Computational Science and Engineering. It has been an absolute honor to be associated with this course, and I'm grateful for the opportunity to learn along with this course and to share some of my insights with fellow learners. And this was the last session for the course. So I'm grateful for all participants who found time every week and tuned into these sessions. Again, I'm grateful to Professor Ashok Dey, who chose me to assist him in this course, and I hope I have met his expectations. Thank you very much. Uh, I am Sourav Goswami from the Department of Mechanical Engineering at IIT Bombay. Thank you.